Think about drawing a simple circle. Pretty basic, right?
Sure.
Now imagine that circle twisting, morphing, becoming part of some, I don't know, complex sculpture or maybe an intricate building design.
Right. It's amazing how complex forms start simple.
Exactly. And it all starts with this fundamental language of shapes
Mm-hmm.
and right at the heart of it all, vectors.
That's spot on. Vectors are really the unseen force, you could say. They let us define and manipulate geometry in the digital space.
So for this deep dive, we're really digging into a data and design workshop that explored exactly this.
Yeah, how we move from those basic building blocks you mentioned, vectors, but also lines, polylines, curves to create really sophisticated forms.
And the workshop used tools like Grasshopper and Python.
That's right, whole mix of things.
We've got quite a bit of material from this workshop. Videos, code examples.
Yeah, lots to work with.
So our mission here is to really pull out the core principles. What's the essential stuff you need to know? And hopefully reveal how these sometimes abstract geometric ideas have really practical, maybe even surprising applications.
And, we understand that you listening might be coming at this from different angles. Some might know coding, some more design software, maybe neither.
Right.
But don't worry, we're aiming for clarity here, trying to get those aha moments where the complex stuff just clicks.
Okay, let's jump in. Vectors. You said they're essential. Why? What makes them so fundamental?
Well, basically, a vector is just a way to describe movement or direction in space. It's got a start and end, so it has a length, a magnitude.
Like an arrow pointing the way?
Kind of, yeah. Think of it as the simplest instruction for, defining the relationship between 2 points. And the workshop really hammered this home. These simple directions are the absolute bedrock for creating and controlling digital geometry.
So it's how you build up complexity from, well, simplicity.
Exactly, the first step.
Okay, vectors connect places. But what are these places? Where do we start?
Points, simple points. In a 3D digital space, a point is usually just 3 coordinates, x, y, and z.
Okay.
The workshop notes mention these often correspond to indices 0, 1, and 2 in programming lists or arrays. It's a basic way to, pack coordinates together.
Right, like a digital address system, XYZ. Got it. So what happens if we connect 2 of those addresses?
Then you get a line, or technically a line segment. It's just the most direct connection between 2 points, a start and an end.
Simple enough.
And from that simple definition, you can suddenly do a bunch of basic things, right? Draw it, figure out its length, find the exact middle.
The midpoint, yeah.
The workshop even showed a little code snippet, creating a line just by accessing the coordinates of 2 points, mentioned using index 1 after the 0 index, typical programming stuff.
So it all comes down to knowing the numbers for those start and end points.
Pretty much.
Okay, 2 points, straight line. What if we chain them together? Like a whole sequence of points connected one after the other.
That's a polyline. Think of it like a connected chain of straight line segments.
Okay.
It's defined by an ordered list of points, the vertices, where each point links one segment to the next.
And these are used a lot in things like maps.
Hugely important, yeah. Especially in GIS, Geographic Information Systems. The workshop pointed out how GIS data uses these all the time for paths, boundaries, point and line string and polyline and polygon and multiple polygon, all that stuff.
So polylines are like connect the dots with straight lines. But what if we want smoother shapes?
Yeah.
Curves.
Exactly. That's where curves come in. They're definitely more sophisticated. They allow for those smooth, non-linear forms we see everywhere.
And how are they defined? It's not just start and end points anymore, is it?
Not usually, no. There are a couple of main ways. You can define them with math equations. That's called a parametric definition. Or you can use control points that sort of influence the shape.
It's control points, like the handles you drag in design software.
Yeah, precisely. Those are often used for Bézier curves. The workshop mentioned both types. Function curves, like using a cosine wave, and those Bézier curves manipulated by control points.
Parametric curves. That sounds a bit mathematical. Are they really that important?
Oh, absolutely. Their power lies in their mathematical precision and just how widely applicable they are. The workshop stressed they're fundamental to CAD software like Rhino. That's how it thinks about curves.
Yeah.
But it goes way beyond CAD. They're used in web graphics, HTML Canvas, WebGL. The workshop called it just pure math. Understanding the parameters gives you incredibly fine control.
Way beyond just connecting points.
Right. The workshop even showed briefly how you can generate these smooth shapes directly from mathematical functions.
And the other type, Bézier curves, those are the more visual ones.
Yeah, they often feel more intuitive for designers. You grab those control points, maybe they're handles, and you directly shape the curve. The workshop mentioned RhinoScript syntax has an edit point function, highlighting how moving control points is a key way to tweak these curves, even with code.
Okay, so lines, polylines, and now these more flexible curves. What about common shapes like circles, arcs, ellipses? Are they special types of curves?
Essentially, yes, they're specialized curves, each with its own specific defining parameters. A circle, for instance, can be described really elegantly using sine and cosine.
Ah, trigonometry flashbacks.
Yeah. An arc is just a piece of a circle, right? Defined by its center, start and end angles, or maybe tangents.
Okay.
And an ellipse, basically a squashed or stretched circle. You define it with a center, two different radii, major and minor, and maybe a rotation.
All right, so we've got the basic geometric building blocks laid out. How do we actually start using them? The workshop talked about tools like Grasshopper and Python.
Right, this is where it gets practical. Grasshopper was described quite aptly, I think, as a visual playground.
I like that.
It's this environment where you connect these visual blocks, tweak sliders for parameters, and see the geometry change right in front of you. Super interactive.
So you get immediate feedback. Great for learning.
Definitely. But the workshop also gave a little warning.
Ah.
Yeah, not to get stuck in the Grasshopper component. The advice was to come out the universe.
Come out the universe. What does that mean?
It means understanding what's underneath those components. Grasshopper is fantastic visually, but the logic is still code, still math.
Oh, okay.
So the idea is to grasp the fundamentals, the pure math, the core math, so you're not just relying on pre-made blocks. That way you can apply the ideas anywhere, not just in Grasshopper.
Understand the engine, don't just drive the car. Makes sense.
Exactly.
And I guess that leads us to Python scripting, getting closer to that engine.
Precisely. Python, especially used inside Grasshopper, gives you way more custom control. You use libraries like RhinoScript syntax, often just called Rs, to write your own scripts for specific geometric tasks.
So you can build your own tools, essentially.
Yeah, things that might not exist as a standard Grasshopper component.
Now, the workshop mentioned the Rhino API has two levels of access, RhinoScript syntax and something called RhinoCommon. What's the difference there?
Yeah, the way the workshop framed it was quite helpful. RhinoScript syntax is the easier one, more user-friendly. It works with object IDs, these vids. They compared it to playing at the elementary school level.
Okay, accessible.
RhinoCommon is the deeper level, lower level, more comprehensive. It gives you direct access to the objects themselves, their properties, methods, much finer control, but steeper learning curve. That was compared to the level of a graduate researcher.
So RhinoScript syntax for quick tasks, RhinoCommon for the really complex or performance-heavy stuff.
That's a good way to think about it. And the key thing is that Rhino and Grasshopper are often passing these object IDs back and forth.
Oh.
So understanding the inputs and outputs for functions in both APIs is critical. The workshop really stressed checking the Rhino developer docs. They used the simple add line example. It needs a start and end point as input. You have to know that.
Right, know what the function expects.
Yeah, and they even showed in Python how you might get an object reference versus just its ID, and how you'd use something like R's point coordinates to actually get the XYZ numbers from a point object you've created.
It sounds like just managing all this geometric data is a big part of it. The workshop mentioned data structures.
Definitely. How you organize your points, lines, whatever, is crucial.
Yeah.
Are they in a simple list, a nested list maybe, to group things?
Right.
How you structure that data really affects how easy it is to work with in your code.
And it's not just the structure, but the order you do things in, right?
Yeah.
Code is a process.
Absolutely. Writing code for geometry is sequential. Step 1, step 2, step 3. Each step potentially changes your shapes. You have to understand that flow.
Which really points to needing hands-on practice. The workshop encouraged learning by doing, didn't it?
Massively. Experimentation is key. Try stuff. Change values. See what happens. The instructor even mentioned using code comments like the control/shortcut to explain your own code to yourself as you go.
Good tip.
It's all about active engagement, seeing how these abstract ideas actually look and behave.
Okay, basic shapes, tools to work with them. Now, what can we actually do? The workshop went through a bunch of geometric operations.
Yeah, this is where the fun starts, the creative part. One of the most basic things is just measuring distance between points.
Simple enough.
But what was cool was how the workshop linked that to, like, everyday human behavior. How far are you willing to walk based on distance, or if the weather's bad?
Hmm, that's a great connection. Makes it less abstract.
Exactly. Shows the real-world relevance.
Okay, distance. What else? What other fundamental operation?
Finding the closest point on a curve to some other point in space, that's a really common one.
Okay.
And this operation usually gives you back something called a t-value.
A key value.
Yeah, it's basically a parameter. It tells you where along the length of the curve that closest point is. Often it's a number between 0 and 1, like a percentage of the curve's length.
The workshop had that quote about it, right?
Yeah.
The one explaining the intuition behind getting the t value from a projection.
Exactly. It's about understanding that the system finds the closest spot by projecting your point onto the curve, and the t-value is the address of that projected spot along the curve's own parameter space.
And once you have that t value,
Yeah.
what can you do with it?
That's the powerful part. The t-value lets you do curve evaluation. You plug that t-value back into the curve's definition, and you can find out all sorts of things about that specific point on the curve.
Like its exact coordinates?
Yes, its coordinates, but also its tangent, the direction the curve is heading right there, and the normal, which is perpendicular to the tangent.
Wow. Okay, so it's like having a super precise address and also knowing the street's direction and like the direction pointing straight up from the street at that exact spot.
That's a great analogy.
Yeah.
Very precise local information.
Cool. The workshop also talked about taking apart and putting together curves and polylines.
Right, basic manipulation. You can split or divide a curve or polyline into smaller pieces. Maybe you want a certain number of segments or segments of a specific length, or you use those t-values to split at exact points.
Okay.
Then there's exploding a polyline, breaking it into its individual line segments. The workshop mentioned eyes explode curves for that.
And the opposite, putting them back together.
Yep, joining, combining separate lines or curves into one. Ayer's join curves was the example function there. And also trimming, cutting curves where they intersect other things.
So you can really chop up and rebuild geometry. What about just moving or changing shapes generally?
That's geometric transformations.
Hmm.
Rotation is a common one, used for things like spirals. But also translation, just moving stuff, scaling, changing size, shearing, mirroring. Lots of possibilities.
Though sometimes you might have data, like from a sensor, just a cloud of points, and you want to find a smooth curve that fits it. The workshop mentioned fitting curves.
Yeah, that's a really powerful technique for finding patterns. Linear regression, finding the best straight line, is a simple example.
Yeah.
The workshop used the analogy of a ball's trajectory. You track points where the ball was, then fit a curve to understand the whole path.
Using math to go from scattered points to a continuous shape. Makes sense.
Yeah.
What about creating patterns? Geometric pattern generation.
Oh, yeah, lots of cool stuff there. Generating grids of points, drawing polygons. And they made a good point about vertex order being important for polygons to draw correctly.
Ah, otherwise it folds in on itself or something.
Exactly. They briefly mentioned Voronoi diagrams, too, patterns based on closeness to points, and showed creating a cogwheel or sawtooth shape by moving points on a circle differently if they were even or odd in the list.
Clever.
And generating 3D shapes like cones and spheres, either using parameters or transformations.
The workshop also mentioned attraction and repulsion. How does that work?
It's an algorithmic thing. You set up rules where points might get pulled towards certain attractor points or pushed away from repulsor points based on distance.
So you can create these complex, almost organic-looking patterns.
Yeah, generated by those simple rules.
And mapping latitude-longitude onto a sphere that's a very direct application.
Definitely. Connecting real-world coordinates to a 3D geometric form.
Then there was circle packing. Sounds like a game.
It kind of is computationally. The idea is to fit as many circles as possible into an area without them overlapping.
How does the algorithm do it?
Typically, it tries placing circles randomly, then checks if the new circle bumps into any existing ones. It does that by comparing the distance between their centers to the sum of their radii.
If the distance is less than the combined radii, they overlap.
Exactly. If there's no overlap, it keeps the circle. Repeat. The workshop noted it's interesting to track the failures, too, when it can't place a circle.
Right, tells you how dense the packing is getting. Okay, moving on from patterns. Optimization. What's that about in design?
The example given was pretty neat. Find the width and height of a rectangle to get a specific target area, say 471, within a certain tolerance, like plus or minus 5.
How would you solve that?
The algorithm just tries random dimensions iteratively, checks the area, and keeps going until it finds one in the target range. They found something like 29 by 16 worked.
So it's like computationally searching for a good enough solution.
Yeah, exactly. A guided search. And then they briefly mentioned genetic algorithms as a more advanced way.
Genetic algorithms. Sounds biological.
It's inspired by evolution, yeah. You start with many possible solutions, see which ones work best according to your goal, keep the good ones, and introduce small random changes, mutations to create the next generation of possible solutions.
Huh.
The example was finding A, B, C, where A times B plus C equals 200. The algorithm iterated, solutions got better and better, reaching a score like 0.99 accuracy.
Wow. So it evolves toward an optimal answer.
Hmm.
Fascinating. Okay, then things got a bit more intense with a deep dive into curves using differential geometry.
Yeah, that touches on some more advanced math for understanding curves in 3D space very precisely. Concepts like the tangent vector.
The direction of the curve.
Right, and the normal vector, perpendicular to that, and the binormal, perpendicular to both. Together, they make the Frenet frame, like a little local coordinate system that travels along the curve.
Okay.
And also curvature, how much the curve is bending. Understanding this stuff helps you do things like orienting shapes smoothly along a complex path, like putting circles along a curve that perfectly follow its twists and turns using that Frenet frame.
So really understanding the fine-grained details of the curve shape at every point. And finally, ribbon structures. What are those?
Imagine taking a 2D shape, like a line or a small profile, and sweeping it along a 3D curve to create a surface, like a ribbon.
Ah, I see.
The way that shape orients itself as it sweeps is often controlled by the curve's tangent and normal vectors using that differential geometry stuff. The workshop mentioned a custom C# implementation, a curve utility with a getCurveRibbon function, showing how you can bundle complex operations into reusable code.
Okay, wow. We've gone from basic vectors all the way to custom code for generating complex surfaces along curves. That's quite a journey.
It really covers a lot of ground.
So for someone listening, trying to absorb all this, what are the really crucial takeaways? What should they focus on next?
The workshop wrapped up with some really solid advice. Number 1, practice. Hands-on. The instructor was really passionate about this, saying, break things, mess things up, that's how you learn. Keep thinking while you do it.
I love that. Don't be afraid to experiment, even if it means making mistakes.
Absolutely. The second big thing was understanding the why behind the how. Don't just use the tools. Understand the underlying vector math.
Right, the fundamentals.
Yeah. The instructor really wanted people to realize they could, in theory, do all this stuff with just the math, even without the fancy APIs. That deeper understanding is more valuable, more transferable.
So it's not just about knowing which button to click in the software.
Exactly. It's about grasping the concepts.
What other skills do they highlight?
Being able to read code and, crucially, API documentation. You have to be able to understand what a function needs, inputs, and what it gives you back, outputs. The instructor was very direct. You need to be able to read this.
Makes sense. You can't use the tools effectively if you can't read the manual.
Right. And related to that is developing computational thinking, breaking down big problems into smaller, manageable steps. That's a skill you build over time with this kind of work.
There was also a quick mention of AI in coding.
Yeah, a useful but cautionary point. AI can help write code, for sure, but you absolutely need to understand the code it generates.
You can't just blindly trust it.
No way. You have to be able to debug it, change it, and ultimately you're responsible for it. The workshop stressed that. AI can help, but the responsibility is yours.
Good warning. And the learning is ongoing, right?
Hmm.
Homework was framed as continuing case studies.
Exactly. Keep looking at real-world examples, see how people are using this stuff, and build your own concept map. Visually connect the dots between points, lines, curves, surfaces, operations. See how it all fits together for you.
Okay, so let's try to sum up the really key takeaways. Master vector fundamentals. Understand geometric relationships and operations. Learn to think computationally. Be responsible with tools like AI. And remember, these ideas apply broadly.
That's a great summary. These aren't just Rhino or Grasshopper skills. They're fundamental concepts for digital geometry pretty much anywhere. Architecture, art, design, visualization. It opens up a huge range of possibilities.
So as we wrap up this deep dive on vectors, lines, and curves, hopefully you're feeling a bit inspired. Inspired by the sheer potential packed into these basic building blocks.
Yeah, how simple ideas lead to complex results.
Think about how you could combine and manipulate these elements to create something new, something intricate, maybe something unexpected. We really encourage you to explore this stuff further.
Definitely. Try out visual programming, maybe dip your toes into Python scripting if you haven't already.
because understanding these basics really does unlock a whole universe of creative potential.
It gives you a powerful new way to think about and create forms. So keep experimenting, keep asking questions.
And keep building.